My talk is called A Simple Correspondence Between Stochastic Processes and Quantum Systems. It's based on a bunch of papers, and I'll explain the Magritte painting in a little bit. All right, outline of the talk. I'll start with an introduction. Then I'll define what I mean by an indivisible stochastic process, which will play a central role. Then I'll lay out this correspondence that is the central point of the talk. And then I'll connect all of this with causal locality and Bell's theorem, and then I'll conclude. Introduction. So I'm going to start actually with a survey that I did. I exploited my role as running the PhD program in physics at Harvard. This is a survey I did of the 37 incoming physics PhD students on some foundational questions in physics. The ones I want to call your attention most to are the upper left, the measurement problem and quantum theory. You can see that 24.3% plus 18.9%, so roughly low 40s percentage of incoming students regard the measurement problem, which I'll talk about, as either a major or minor problem in quantum mechanics. I'll talk about that. But the plurality of respondents say that it's just not something they feel they know a lot about. And hopefully we'll do something a little bit about that today. The one on the right isn't about quantum mechanics. It's just this old question about, does time really flow, or is the flow of time merely a severally persistent illusion, as Einstein once famously wrote in a letter? It's curious that about half of them agree with Einstein, but that may be just because I included Einstein's name, and who wants to contradict Einstein?
So what did Einstein say, sorry?
It was in a letter to the widow of a dear colleague, in which he said, commenting on the passing of this colleague, that don't worry, time is but a stubbornly persistent illusion, right? That the departure of the colleague was, yeah. Anyway, but the bottom one, what's your preferred interpretation of quantum theory, I think is probably more relevant to today's talk. About half of the respondents, the big blue and red portions of the chart, are basically students who subscribe to something like the standard conventional view of quantum mechanics. We'll talk about that. The Copenhagen or orthodox interpretations, there are some subtle differences between them, but I'll make that clear later. The next biggest category is people who believe in the many worlds or Everett interpretation of quantum mechanics, and basically everything else is just a very thin sliver. Sad to say that includes the pilot wave folks. All right, I'm going to move on. I'm going to start by talking about the wave function paradigm. This is the story that one often tells about what quantum mechanics is about. So in most textbook treatments of quantum theory, you take the basic object to be a wave function, which is actually a vector, a kind of vector, a unit norm vector in an abstract vector space called the Hilbert space over the complex numbers. And by axiom, this wave function or state vector changes with time according to the famous Schrodinger equation. Right? Time derivative of this wave function with a factor of I and h bar. H bar is just a matter of getting the units right. The I corresponds to the Hamiltonian operator being self-adjoint. This is an equation that tells you act on the state vector with this thing called the Hamiltonian. It's a self-adjoint operator on the Hilbert space, and it generates the evolution of the state vector. Right? Sometimes one instead takes the basic object to be what's called the density matrix, which I'll talk about a little bit later, or more abstractly, what's called a state map or a linear map on a C-star algebra, but I won't say very much about that in this talk. Then there's a host of other axioms that I'll review briefly in a moment that provide an instrumentalist algorithm for using wave functions to calculate probabilities of measurement outcomes. And much of the interpretive debate today lies within this wave function paradigm. People talk about, what is your view on the wave function? Clearly, quantum mechanics is about wave functions. What's your view on it? Is the wave function epistemic, merely a question of our knowledge and belief? Is it ontological, a physical feature of reality? Is it nomological? Is it really expressing some feature of the laws? Is it something else? And whether or not we should supplement the wave function with other things, it's like so-called hidden variables. Okay. Now, where did this wave function paradigm come from? So in 1925, Heisenberg, Born, and Jordan took the physical picture out of quantum mechanics and replaced it with an abstract theory of matrices, which became known as matrix mechanics. But then, a few months later, in 1926, Schrodinger introduced his undulatory mechanics, which was a formulation of quantum mechanics in terms of what we now call wave functions. Schrodinger introduced the wave function, and he regarded the wave function as a physical object. Now, what's weird about wave functions is they don't live in physical space, and I'll have some more to say about this in a little bit. Nonetheless, he took very seriously that wave functions were physical objects, at least for 2 years, and then in 1928, he recanted that view and said, actually, my mistake. But by then, the cat was out of the barn, and now people talk about quantum mechanics like it's all about wave functions. There are other people who work on other formulations of quantum mechanics, certain variants of the Copenhagen interpretation, quantum Bayesians, and maybe people who work with C-star algebras who don't agree that the wave function is actually physical, but there tend to be a minority. Most people operate within this wave function paradigm. Again, this is the notion that quantum theory is about wave functions or density matrices, and they build everything else on top of that. So now one hears talk about whether the wave function is complete or not, or if there are hidden variables in addition to wave functions, or if one is a psi epistemicist, you regard the wave function as purely a matter of knowledge or belief, or a Scientologist, that's literally what they're called, and you believe that wave functions are physical objects. This is the language of a paradigm introduced by Harrigan and Speckens in a paper in 2010. All right, what are the goals of my talk? The main goal is to argue that no, in fact, every quantum system is to be understood as a kind of a stochastic process called an indivisible stochastic process, unfolding in an old-fashioned configuration space. Just a system bouncing around in some stochastic way with no fundamental role for wave functions or density matrices. There are some more goals of this talk. I'll define what an indivisible stochastic process is. I'll give a correspondence between indivisible stochastic processes and quantum theory, hopefully with some interesting applications to stochastic modeling. I'll describe some concrete examples, including a classical analog model of a quantum system corresponding to a qubit that may be hopefully realizable in a laboratory. And along the way, I'll demystify and deflate some of the more exotic claims about what's going on in quantum mechanics, about things like interference and entanglement and decoherence and the measurement process. And finally, I'll introduce a new nomological, law-like definition of what causal influences are, and I'll argue that under that definition, quantum theory is local, contrary to what is usually taken to be the conclusion of Bell's theorem. So what are the textbook axioms? I'm not assuming everyone here knows the axioms of quantum mechanics. So axiom 1, like I said, each state of a quantum system is represented by a unit norm state vector or wave function, or more generally by a positive semi-definite unit trace density operator, also called a density matrix, in or on a Hilbert space of some dimension h. Hilbert space is a complete inner product space of the complex numbers, usually assumed to be separable. 2, a closed quantum system evolves according to a unitary time evolution operator, U of t. Unitary means its adjoint is equal to its inverse, or in most circumstances, in typical circumstances, not all, but in special circumstances when the requirements of Stone's theorem hold, you can express this in differential form as the Schrodinger equation in terms of a self-adjoint Hamiltonian that I introduced earlier. Right? Axiom 3, each observable feature of the quantum system is represented by a self-adjoint operator, A, equal to its adjoint, whose eigenvalues, whose spectrum of eigenvalues are the possible numerical measurement outcomes that you can measure. 4, the Born rule gives a mathematical rule for taking the state vector or density matrix of the system and an observable and pushing them together and generating a prediction for the probabilistic measurement expectation value of that observable. You get a statistical average of measurement outcomes over measurement probabilities. And 5, immediately after the measurement has been done and you get one answer according to a probability given by the Born rule, the quantum state collapses in such a way to ensure that a subsequent measurement done immediately after will yield the same results. That's the famous collapse axiom. The three axioms 3, 4, and 5 in this breaking up of the axioms, these are the so-called measurement axioms that connect the abstract Hilbert space formalism to physical things you'll actually see. Note, axiom 5, there is some lore that axiom 5 can be explained away using a thing called decoherence that we'll talk about later, and I will explain why that in fact does not work and it does not get rid of axiom 5. All right, so the problem with the axioms of quantum mechanics is they are either incomplete or inconsistent. This is not like a philosophical problem, it's a basic logical problem. And this problem with the axioms is typified very nicely by what's called the Wigner's friend paradox, which has an interesting history that I won't get into. It's been generalized in a whole bunch of ways, some good, some not good. But the original Wigner's friend paradox is quite helpful here. So let W be Wigner, who is an observer who remains outside of a perfectly sealed box. Wigner's friend, WF, is inside the sealed box along with some quantum system, and Wigner's friend is going to do a measurement on that quantum system sealed up in the box. Okay? The question is, we've got two observers. Do we activate the collapse axiom 5 or not? The textbook axioms are non-committal here, right? There's just this basic incompleteness. Do we activate the axiom or do we not activate it? We've got two observers. And so we basically have four possibilities. One is, yes, invoke it. But if you invoke it, now you have to answer, what do you mean by a measurement? Which processes count as a measurement? If Wigner's friend is not a person but is like, a bacterium, does a bacterium count as a thing that does a measurement? What about a buckyball? Can a buckyball do measurements? You run into this basic question about where is the line between measurement and non-measurement. Do we or do we not activate axiom 5? This is called the measurement problem. This ambiguity is called the measurement problem. What's even worse is that measurements are a very narrow class of phenomena, a very narrow category of phenomena, right? Not everything is obviously a measurement. What about when people fall in love? Is that a measurement? What about when gases are mixing in the primordial early universe? Is that a measurement? What about when birds are foraging? Is that a measurement? There's lots of phenomena out there in nature. Are they outside the axiomatic ambit of quantum theory or not? So I call this the category problem. How do we account for the larger category of phenomena, given that the axioms only talk about measurements? All right, that's option 1, A. Option B is, yes, we have a problem, but maybe we can avoid it by not invoking the collapse axiom for Wigner on the outside of the box, but still assuming that somehow there is a unique outcome of the experiment inside the box. Well, if you do that, then that unique outcome that's inside the box that's not reflected in the overall wave function is literally a hidden variable, a variable information that is not accounted for by the wave function. Okay? Option C, replace the collapse axiom with some other kind of process like a spontaneous dynamical collapse process The spontaneous dynamical collapse models have been studied. They're currently being studied. They got a lot of problems. I can't talk about them in this talk. And maybe option D, don't assume there's a unique outcome. All the possible outcomes occur in some sense, and we're in some kind of many worlds type picture of the universe. But then what does probability even mean when everything happens and everything is deterministic? I'm not going to wade into that. What I will say is that B is going to be the point of my talk. I think this is the most promising direction. All right. Let's revisit a paradigmatic thought experiment that was actually eventually done, the double-slit experiment, often described as the experiment that will tell you what's really going on in quantum mechanics. At least get across to you what's happening in quantum mechanics. Okay? So to be clear, this formulation of quantum mechanics I'm going to present is not about any one kind of system. It's not limited to systems of particles. But this single particle example will be helpful in explaining what's going on. Okay? So in the double-slit experiment, one imagines sending particles, one at a time, very important, one at a time, toward a wall with two slits in it and observing where the particle arrives on a screen. Now, why do we send particles one at a time? For those of you who know what a configuration space is the set of all possible ways a system can be. And when you've got one particle in 3D space, the configuration space is 3D. It looks just like physical space. And that makes this picture nice and intuitive. But the moment you've got more than one particle, now the configuration space is 3 times the number of particles dimensional. So if you've got 10 particles, it's a 30-dimensional configuration space, and good luck taking this picture and making it intuitive, right? After all, where are the slits even supposed to be in a 30-dimensional space? I don't know, okay? So I'm just bringing this up because next time someone's like, let me explain quantum mechanics to you, I'm going to do a two-slit experiment. I want you to feel a little bit guilty about using this example, okay? But here's the setup. Particle approaching the two slits. The slits are assumed to be close together. Let's let A be a variable that generically denotes random initial conditions. B, which slit the particle goes through, is C, where it lands. Now you do this experiment, okay? And the way this experiment is described classically, in a classical textbook, this could be like first chapter of volume 3 of Feynman's lectures or wherever, this assumption is made implicitly. It's never made explicit, but it's implicit. This is the statement that, reading from right to left here, the conditional probability of the particle entering the bth hole given the initial conditions A, multiplied by the conditional probability, given that it went through the bth hole, that it lands at the cth location on the screen. You take those things, you multiply them, you sum over B which hole it is, and this gives you the overall conditional probability for what part of the screen C it lands on given the initial conditions. This is not a truism of probability theory. This doesn't follow from the general rules for marginalization. It entails a hidden assumption, a Markov or divisibility assumption, which we're going to challenge in this talk. Okay? If you do make this assumption, now, usually when this problem is addressed classically, one doesn't assume probabilities at all. One uses deterministic dynamics, but a deterministic dynamics that still satisfies this basic property that you can divide up the dynamics at the holes. If you make this assumption, you get the following prediction of landing sites. Okay, you get this prediction of landing sites. Why do you get this prediction of landing sites? It's a blend of two different distributions, right? Blend of these two distributions. And in fact, when you do this experiment with stones, with macroscopic objects, pebbles, you in fact get this pattern. Okay. But if you do this experiment with electrons, right, you send electrons over many repetitions, one at a time, very important, one at a time, you get the following pattern of landing sites. This does not look like the pattern we saw before. In fact, it's best described by this pattern, which looks like a wave-like interference pattern. So what does this mean? Does it mean that each particle is really a Schrodinger wave or something? The wave goes through both holes, and the particle goes through both holes or something like that? Well, again, the moment you've got two or more particles, it's not 3D space. The wave doesn't live in 3D space. The wave lives in high-dimensional configuration space, and I have no intuition for what this is supposed to tell you. But at the end of the day, no, right? The point of this talk is going to be you do not have to assume that there is, in fact, a physical wave here. I'll show that you can account for this pattern merely by allowing the dynamics to be non-Markovian and indivisible, to not assume that condition that we implicitly assumed, or that is implicitly assumed in most textbook treatments. Okay, that's the introduction. Now let me talk about what an indivisible stochastic process is more rigorously. An indivisible stochastic process is a simple generalization of a stochastic process or even a non-Markovian stochastic process. So here's what it consists of. Here are the axioms. There are fixed ingredients of this model. The fixed ingredients are the following form. On the level of kinematics, there is a configuration space, just the sample space, the set of all possible ways your system can be. That's a fixed feature of the model. And the dynamics is another fixed feature of the model. Given times t and t naught in respective index sets, capital T and capital T naught, there is a first-order conditional probability map gamma, right? That takes in the domain is the Cartesian the Cartesian product of the configuration space. It takes in an initial configuration at t naught. It takes in another configuration at time t. It takes these two things and it maps it to the conditional probability. The conditional probability of the system is in the first configuration at the time t naught, conditioned on that it is then going to be in the configuration of later time t. So it's a conditional probability. These special times in the second index set T naught, the times that you can condition on, are called division events. Then there are contingent ingredients, ingredients that will differ every time you instantiate this model and run it in the real world. They can differ between runs. For times T in the larger index set T, there's some probability distribution P of T. This is just the instantaneous probability distribution of which configuration the system is in. And we expect that every time we run the model, this could be a different probability distribution depending on initial conditions. Okay? These are the new axioms. These replace the axioms of quantum mechanics. They're axioms about physical things that do things according to probabilities. Okay? Importantly, there's also a linear marginalization rule. You give me the probability distribution at T naught, and then I can predict the probability distribution at T by convolving with these conditional probabilities. And this is a linear relationship between these two. This linear relationship will be very important and will explain why evolution in quantum mechanics is linear. It's not an axiom anymore. We'll derive it. Okay? Here, it's just a consequence of how conditional probabilities work. But we'll see that this is what leads to the linearity of time evolution in quantum mechanics. Let me say a word about the history of this notion of indivisibility. Indivisibility is a simple and remarkably new idea. You think of it as a failure of iterativeness. It originated in the theory of quantum channels by Ignacio Sirac and Mikhail Wolf in a paper in 2008, which preprint was 2006. It was first applied in a classical context, not to quantum systems, a classical context, as late as 2021 in a review article by Simon Mills and Kevin Modi. And it was like a throwaway line in like figure 5 on like page 15 of this paper. It was just like this like minor note. They didn't even really talk about it. That's how recent this idea is. It's remarkable that a simple idea like this is so recent to vintage. But the basic idea is, like I said, you have this dynamical map, this conditional probabilities. The brown ones are the laws. I'll use brown color for things that are actual laws. We have a law that tells us the conditional probability to get from T naught to anytime T prime. We have a law that takes us from T naught to anytime T. And the question is there some purple stochastic map that takes us from the intermediate time T prime to the time T that basically interpolates between these times, that allows us to divide the evolution up from T naught to T into evolution from T to T prime and then from T prime to T? And the answer generically is no. This model will not in general have a purple map like this. No such map will generically exist. Even if you can define a matrix that will serve in this role, you'll find that it has negative entries or is just not a well-defined stochastic matrix. So unlike for a textbook non-Markovian stochastic process, it's important to note that I'm not going to define any higher order conditional probabilities. I'm not going to specify them in the model, so this is like a generalization of non-Markovian stochastic processes. You can think of this, roughly speaking, as like a non-Markovian model of infinite order, right, where there's just an arbitrarily long amount of memory, and we're not going to go to the trouble of specifying all those higher order probabilities. It's clear why people didn't study these systems before, because it would have seemed insurmountable to define like an infinite tower of conditional probabilities, but we're not going to have to do that. Okay? So here's an example of how this can show up in a very simple system. Okay? We're going to consider the simplest kind of discrete time deterministic process. We've got n configurations that deterministically transition in time steps delta t, okay, by permutation. So, for example, every time step delta t, we go from configuration 1 to 7, from 7 to 3, from 3 to 2, from 2 to 13, to 5, etc., until eventually we get back to 1 and then 7 and then 3, because it's a finite configuration space. Okay? We can represent the different states of the system using basis vectors in an n-dimensional configuration space, n-dimensional vector space. So these are my n basis vectors. Each one represents one of the configurations of the system. And then I can represent the dynamical law as a permutation matrix. There's an n by n matrix, and you just act repeatedly, and it just takes you to the next state. A permutation matrix, as a reminder, is just the identity matrix with rows permuted. So it's a matrix of zeros and ones with a 1 in every column and every row, and otherwise all zeros. It implements this evolution. You just repeatedly act with this permutation matrix. Well, now this is just math. A permutation matrix is unitary. All permutation matrices are unitary, right? And actually, you can go farther and show that because acting n times gives you back the identity matrix, the eigenvalues of a permutation matrix have to be roots of unity. Wait, that's just an aside. But for t, any smooth parameter, so t is now smooth time, not discrete time, smooth time, I will take that permutation matrix and I will set it to the power t over delta t. Okay? This is now a power, an exponent that's a smooth function of time. And because sigma was unitary, this power exists and is still unitary. It defines a unitary matrix, U, that I can think of as taking me from 0 to an arbitrary time t, okay? And still unitary. Okay, I can take each of the individual entries, the ijth entry of this n by n unitary matrix. It's in general a complex number. I will mod square it, and it will give me a non-negative number, and that will define the entry of this conditional probability map. So I'll get an n by n matrix whose entries are, by construction, the mod squares of the corresponding entries of an n by n unitary matrix. And by definition, it's called a unistochastic matrix, a concept first introduced by Alfred Horn in a paper in 1954. This is not a quantum process I started with. I started with a completely boring classical process, and yet I've introduced a quantum-like formalism. And so I have this matrix now. This is a matrix whose entries are non-negative. You can show that the columns sum to 1, the rows sum to 1. So this is called a doubly stochastic matrix, and it defines an indivisible stochastic process in line with the axiomatic definition I presented. So we've interpolated the discrete time process with a smooth in-time process that is a unistochastic process, but we've designed it in such a way that every time we go an integer amount of time steps, if t is ever an integer amount of delta t, then our stochastic matrix reduces to the original permutation matrix. The probabilities all disappear. So basically, we have a probabilistic process between the time steps, and each time step, the probabilities disappear. But the particular kind of probabilistic process that we've used to interpolate it is an indivisible stochastic process. So here's a concrete example. Okay? Now, this unitary matrix is unitary. So I can take its adjoint, I can multiply them together in this way, and I can define a purple matrix that takes me from t prime to t. Okay? And then I have this convenient composition law that I said didn't exist for an indivisible stochastic process, and it does not. But the unitary matrices satisfy this. Okay? But the indivisible stochastic process will fail to have this property. So it may look like the first property implies the second, but remember, we're mod squaring entries to get from u to gamma. And the mod squaring of the entries screws up the ability for it to hold for gamma. If you try to do it anyway, if you try to take the purple U matrix, square its entries, and use it to try to define a purple gamma matrix to do this interpolation, which we said you weren't allowed to do, you'll get the wrong answer. And if you compare the correct evolution to the wrong evolution, you get a discrepancy, you get discrepant predictions, and those discrepant predictions are mathematically identical to the interference terms you get in quantum mechanics. So interference is now to be understood not as some exotic phenomena, cats are alive and dead, or something like that, but literally just a recording of the fact that the process is actually indivisible. And interference, and we'll see phase factors in quantum mechanics, are just encoding indivisibility. Okay? All right. Now, that said, the stochastic process will divide at the special integer time steps, where the probabilities disappear, and those are called division events. Those are in that set T naught of division events that a process in general will have some. Okay? And we'll say more about division events as we go. But notice that U here is a smooth function of time unitary. Okay? You can define a Hamiltonian out of it, a generator of the evolution. Right? You can take this unitary, act on your initial vector representing your initial state. You'll get a complex valued n by 1 vector that's your state vector, right? Where E1 is your known initial condition with no initial epistemic uncertainty. And then you can just show that psi satisfies the Schrodinger equation. You can check the Born rule emerges from this, and you get an emergent quantum theory with an emergent Schrodinger equation. Now, if you had some initial epistemic uncertainty over the initial configuration of the system, you can handle that. You take the initial probability distribution. This is an epistemic probability distribution. You distribute it along the diagonal of an otherwise empty n by n matrix. You call it a density matrix at time 0. And you can show that this density matrix, when you evolve it forward with u, becomes a time-evolving non-diagonal density matrix, which obeys the von Neumann equation, which is the generalization of the Schrodinger equation when you have density matrices. And then the Born rule takes this form, which is just a special case of the Born rule that was in axiom 3 of the textbook axioms, where pi is an elementary projection matrix. So we get an emergent quantum theory, and we can also generalize and include density matrices. All right, I'm going to do a completely different classical analog model. This is one that's not just a numerical model, but one that I'm hoping someone in this room can help me implement in the lab somehow. Okay? So this is a classical analog model of a qubit. Consider a black box. By black box, I don't mean literally it's a box colored black, but a black box, I don't necessarily know which of several possibilities is in a particular instantiation of the system. Okay? It can contain either of two possible classical systems. I'll call them A or B. Each has similar looking configurations 1 and 2. For system A, state 1 has the lower energy. For system 2, state 2 has the lower energy, but they have the same energy gap. I'm going to thermally couple this system to a reservoir, but you could also imagine this system having chaotic dynamics instead. That would also work with some coarse grading. But basically, I'm going to, in some way, couple it to a reservoir or something like that with adjustable parameters. Here, I'm adjusting the temperature as a function of time, right? Starting with temperature 0 at the beginning. And then what's going to happen is, the way that thermodynamics works, classical thermodynamics, there's going to be probabilities now associated with the possible configurations of the system. The probabilities will be time dependent because they'll depend on the temperature, which is time dependent. The probabilities are given by this Boltzmann factor. It's the exponential of the negative the energy of the configuration in question as a ratio with Boltzmann constant times the temperature. And so you'll have time dependent probabilities. You can easily take these time dependent probabilities, arrange them into a 4x4 array where there are initial conditions, which just corresponds to whether the system was A or B in the box. If the system was A, then at the initial time when the temperature was 0, it's in configuration 1. Otherwise, it's in configuration 2, if it's system B. And so you get 4 conditional probabilities. And by symmetry, the symmetry of the problem, the conditional probabilities have these equalities. The diagonal entries are equal to each other, and the off-diagonal entries are equal to each other. This matrix is doubly stochastic, and it's just a theorem that every 2 by 2 doubly stochastic matrix is unistochastic, and therefore there exists a 2 by 2 unitary matrix whose entries, when you mod square them, give you this unistochastic matrix, and this leads to a Schrodinger equation that leads to the whole emergent quantum picture. Okay? The original stochastic description is generically indivisible. We don't have a law that breaks down the evolution over time, and you can come up with explicit examples. Here's an explicit, if you set up the time-dependent probabilities so that they're given by exponentials of the form e to the negative t squared over tau squared for some constant time scale, you can prove that this is an indivisible stochastic process. Now, the unitary description has this nice composition property, like I said before. And so what this is telling you is that if your original underlying indivisible stochastic process does not have a nice composition property, doesn't have a nice division property, then introducing a unitary Hilbert space representation lets you have a nice divisible compositional description of the system, but at the cost of having off-diagonal entries and phases and interference and all these artifacts of the fact that the process is ultimately indivisible. Okay? All right. So there's this thing that comes up when people talk about quantum mechanics. It's like, okay, I have a quantum system. It can evolve in various ways. The system kind of evolves in all the ways, and then I have to like blend the results together according to this rule called interference. Let's see how that caches out here. So consider two possible paths you could take in the Hilbert space picture. Okay? They both start in configuration 1. They both end in configuration 2. Path 1 will be the system evolves from configuration 1, stays in configuration 1, and then evolves into configuration 2. In the other path, the system evolves from configuration 1 to configuration 2 and then stays in configuration 2. These are two paths. We would call these two quantum trajectories. And then what you're supposed to do with these things is sum them first as complex numbers, then mod square them, and you get the correct probability. In this system, that works. But we're not saying the system is really taking two paths. The interference here is not saying the system is really taking just one path. And the fact that we have to do this particular rule to get the right answer is precisely because the underlying dynamics is indivisibly stochastic. If you instead try to square each path individually, each complex number individually, assume that each of them is telling you an actual probability of a thing that really happens and add them, you get the wrong answer. This is usually called interference. It's probabilistic interference, and we see that it emerges from this classical analog model. Now, I'm not making any hackneyed analogy here between quantum interference and like the interference of electromagnetic waves you always hear about in like the books. This is actual probabilistic interference showing up in a classical analog model of the qubit. I should say, by the way, this analog model can be generalized to 2 or more qubits, and then you can start to see entanglement and other higher-level quantum effects. Notice, we're not systematically like going through and adding quantum features to a classical model. We're starting with a model that I claim is quantum mechanical, or it has the properties that ultimately describe quantum systems, and then just showing that it exhibits all the features we expect for quantum systems. All right, now I'm going to lay out the actual correspondence. So given any indivisible stochastic process, as defined in that earlier slide, with n configurations, we can take this stochastic matrix gamma, and we can introduce a new n by n matrix with complex entries called theta. Right? This is not a unique process and actually leads to a beautiful and novel form of gauge invariance that I will not have time to talk about. We can talk about it if you've got questions. So theta is not unique, but that won't matter. It's just an n by n matrix of complex numbers that when you square them give you gamma. I'm not assuming it's unitary. However, this matrix satisfies the following sum rule. You sum down the columns and you get 1 because that's how probability works. If it happens that gamma is unistochastic, then by definition I could take theta to be unitary. And then we're off and running, we have a quantum description. But if not, if I don't assume that my original gamma is unistochastic, if it's just some stochastic matrix, actually something really amazing happens. I can take theta, this matrix I've introduced, which is not unitary, I can slice it up column by column, put each column into an otherwise empty n by n matrix, and you can show that this defines n by n matrices that satisfy the rules of being called Krauss operators. Okay? Krauss operators are a well-studied mathematical construction in quantum information science. And there exists a theorem from the 50s, the Stein-Spring theorem, which lets you take such a description, dilate it to a bigger Hilbert space description, bigger in a bounded sense. It's not arbitrarily big. You only have to make it bigger by some bounded amount, and then it's unitary. So even if we didn't assume the system was already unistochastic, we can always, by a Stein-Spring dilation if necessary, implement this as a unitary evolution on a possibly bigger Hilbert space. And that means that every one of these stochastic processes has an emergent Hilbert space representation. And moreover, that linear marginalization rule that I said would be important literally becomes the linear time evolution law for unitary time evolution. Okay. Now, this resolves a number of mysteries. One is, why is the evolution in quantum mechanics linear, at least for closed systems? That's a nice answer. Where do Hilbert spaces come from? That's nice. But if you ever wondered why we use complex numbers in quantum mechanics, this gives a very satisfying explanation. Now, to understand why, you might go, well, how do I know that this matrix U, for the unistochastic case, has to involve complex numbers? Could it be a real orthogonal matrix instead? Well, it's just a fact that for n bigger than 2, unistochastic matrices are not generically orthostochastic. The unitary that you would need for n bigger than 2 generically has to involve the complex numbers. You can't do it with a real matrix. And this means that you inevitably have to have complex numbers if you want a unitary description. Right? So to exploit this theorem connecting these pictures, you'll need the complex numbers or an algebraic construct isomorphic to them. But anyway, Hilbert spaces, as I've explained, are cheap. They're fictions. We can make them appear as needed. So we might as well use the complex numbers, because then we can help ourselves to a huge number of very useful features, which I'm not going to summarize here, but they're listed here. Actually, this is an aside. If you've heard that quantum mechanics is defined for Hilbert spaces over the complex numbers, strictly speaking, that's not exactly true. Because it turns out that there's a certain kind of operation you do in quantum mechanical systems that's important called time reversal. And time reversal operations involve an operator k that complex conjugates, that does not commute with I, okay? Even though I is supposed to be like a scalar. K squared gives you 1, it does nothing if you do 2 complex conjugations, and k anti-commutes with I because it implements complex conjugation. And if you take I, k, and ik, you actually generate a Clifford algebra called the pseudo-quaternions. And in some sense, that's really what Hilbert spaces in quantum mechanics are defined over. So if someone asks you, why is quantum mechanical Hilbert spaces defined over the complex numbers, the answer is, they're not. They're actually defined over the pseudo-quaternions. Okay. But let's go back to wave functions, the Schrodinger equation. So if our density matrix happens to be rank 1, then by arguments that basically are just the arguments I showed before, you can break up, well, if the density matrix is rank 1, you can always break it up as an outer product of a vector with itself. And then you can just show that that vector evolves according to the Schrodinger equation for some Hamiltonian, where again the linearity descends from the linear marginalization rule from before. And so we see from this picture the wave functions and Schrodinger equation and all of that are not fundamental. They're secondary pieces of derived mathematics. They're not primary ontological furniture. They're useful but not central to the theory anymore. And we also see that wave functions are not purely epistemic. They're not just a matter of lack of knowledge, but they encode a blend of epistemic information with the initial conditions together with nomological information, because you can check that actually what a wave function is doing is encoding information in the stochastic matrix. So the wave function has a nomological meaning. It is not physical or ontological any more than Magritte's pipe on the first slide. Ceci n'est pas une pipe, right? You know that pipe on the painting? Magritte wrote that painting in 1929 at rather appropriate time. And people said, what do you mean it's not a pipe? Because ceci n'est pas une pipe means this is not a pipe. He's like, of course it's a pipe. And his answer was, really, it's a pipe? Can you smoke it? Not really a pipe. It's just a representation of a pipe. But I would also make an analogy to the ether. You may know that at some point in history, people thought the electromagnetic waves were waves in some undulating material called the ether. And people really believed the ether was really there. They had all this mathematical description of the ether. And then Einstein comes along and says there is, in fact, no ether. I'm saying there is no wave function. Okay? So the standard unitary Hilbert space formalism, although very useful, right, involves wave functions, is not fundamental. But one of the things it does do is it yields a divisible first-order differential equation for the dynamics. We exchange a clear physical picture for a picture with interference and phases and all this complicated stuff, but then the description now looks divisible. Okay? That's what we're doing. Now, we can also do the correspondence the other way. This was going from a stochastic system and representing it as a quantum system, but I can go the other way. I can take a quantum system and represent it as a stochastic system. If you give me any unitarily evolving quantum system with an n-dimensional Hilbert space, you pick any convenient orthonormal basis you want, and then you write the unitary time evolution operator on that basis, you mod square its entries. This just defines a unistochastic matrix, which defines a corresponding stochastic process. There's not a unique way to do this. There are infinitely many ways to do this, which means that a given Hilbert space representation can describe many different possible classical stochastic processes. But this is not new. This is also like the relationship between classical Newtonian systems and Hamiltonian systems. This is not a problem. It's not a bug. It's a feature. With one unitary description, we can describe an infinite number of different stochastic processes. So this is actually really nice. And also, picking an orthonormal basis is a step we take anyway when you want to define the path integral formulation of quantum mechanics. So this isn't some new thing. Now, are we losing phase information here? Right, this is this question about what the phase information is doing. When we mod square, we're losing phase factors inside these complex numbers. It actually doesn't matter. Remember, those phases are really recording indivisibility. When I go to the stochastic description, I don't need that anymore because the phases now become the indivisibility. But actually, they don't matter at all. Remember, all empirical results come from measurement processes. And now that we have an actual, realizable unistochastic process, we should model the measurement process by putting a physical object in called the measuring device, giving it configurations, giving the whole thing an overall evolution. And when you model the whole thing completely, the phases turn out not to matter. So when do the phases matter? I mean, I can just get rid of the phases? They do actually matter. If I regard the measuring device as a subsystem of the overall indivisible stochastic process, well, by construction, my orthonormal basis is supposed to capture the device's pointer variables, the ones that tell you the measurement outcomes. And by construction, the stochastic dynamics will simply get the measuring device to land probabilistically in one of its measurement readout configurations with the right probability. If I don't want to include the measuring device in my formalism, it's too complicated, I want a measuring device, I'm just going to throw it away and just focus on my subsystem, then I have to keep the phases. And what the phases are doing is encoding the missing measuring device. If I don't want to model the measuring device explicitly, then I do have to keep track of the phases, and I have to use the standard textbook axioms of quantum mechanics. But if I involve the whole measuring device as another part of the indivisible stochastic system, then I don't need the phase factors. That's basically what we're doing. Okay, let me say a little bit more about these division events. So the claim is that we have a framework that, among other things, also allows us to explain why that Markov approximation, the irrelevance of past states, often works so well in applications. So consider a composite system consisting of a subject system and an environment, the system to be studied in some larger environment. Suppose that for each configuration I of the subject system, the environment is a corresponding configuration E of I, to be read as the environment is in a configuration where it has seen the system being in configuration I. And suppose that the overall stochastic transition matrix has somehow yielded this joint probability distribution at time t prime. A joint probability distribution for the subject system and the environment, such that the subject system is in an arbitrary probability distribution, and there's perfect correlation with the result of the measuring apparatus, the environment. The environment has a unit probability of seeing the configuration the system is actually in. Okay? So this is just a standard classical interaction between things. There's no quantum mechanics here. Then if you let the system evolve stochastically and do a classical marginalization over the environment, you can show that the level of the subject system alone, a purple matrix naturally emerges, taking us from time t prime, the time of the interaction with the environment, to any time t. Okay? That is, because of the interaction with the environment and just classical marginalization, a purple matrix emerges that connects time t prime to t. And we see that because of the correlating interaction with the environment, we have a division event at t prime playing the new role of t equals 0. And we expect the division events to be ubiquitous for open systems and noisy environments, and this explains why if there's some rapid timescale over which the environment is checking out of the system, we're going to get what looks like divisible, highly divisible Markovian dynamics. And this gives a way to understand where the Markov approximation comes from in everyday life. Right. It's easy to show that time t prime, the subject system's reduced density matrix, loses all of its off-diagonal entries, becomes diagonal, and that's exactly what decoherence is. So we learn that those off-diagonal entries, again, in a density matrix, these are coherences, which also correspond to superpositions of wave functions or phases. Right? These are a mathematical artifact of indivisibility, and whenever there's a division event and the system becomes momentarily divisible, then we lose those off-diagonal entries. Okay? Right. And coherences, again, are the price for making the dynamics look divisible. And meanwhile, decoherence itself is just the prosaic leakage of correlations into the environment when you look at them through the lens of the Hilbert space formalism. We can also talk about entanglement. And here I'm going to explain what entanglement is with no Hilbert spaces, no quantum mechanics, at least in the usual Hilbert space formalism. Okay, so to begin, note that even in classical physics, when systems are in the middle of interacting, they don't have their own separate laws. There's only a law for the total system. That's going to be the same thing here. So let's consider two subsystems, A and B, that are initially not interacting in any way from time t equals 0 up until just before some time t prime where they will eventually interact. Okay? This means that before t prime, the overall stochastic dynamics of the composite system will tensor factorize, will break up into dynamics for the two individual systems. Okay? But then they interact at time t prime, and because the indivisible stochastic matrix does not divide at intermediate times, it encodes cumulative statistical information, and so it fails to factorize at time t prime, and it will continue to fail to factorize at later times. The two subsystems will fail to have their own separate dynamics at later times. Okay? The two systems will fail to have separate dynamics even if we separate them in space because of that earlier interaction that they had. Right? Right. So the theory just doesn't contain or supply laws for the two subsystems separately. And of course, this already looks like entanglement, but without any mention of Hilbert spaces. Now, if later on, once the systems are far separated, there is a division event, maybe the environment looks at the configuration of one of the two systems, then we will get a division event at that later time t double prime. The overall stochastic matrix will divide at time t prime. There'll be a new matrix starting at t double prime and going to later times t, this purple matrix. And if the two systems are by this point far apart, that purple matrix will tensor factorize, and the entanglement is broken. So we see that decoherence, the interaction with the environment, has broken the entanglement. This is exactly what we expect from entanglement, but without using any Hilbert spaces. This is a completely non-Hilbert space way to understand what entanglement really is. Okay, so I'm getting to the end of the indivisible stochastic discussion. Let me just quickly say that there's also the measurement axioms. We have to worry about how we measure things. I don't have time to go through the measurement process in detail. There's very little time. But let me just say that there's a term that John Bell introduced called beables, not observables, but beables, the way a system can be, which are random variables that describe what a system is truly doing, what configuration it really is in. From our point of view, beables are just random variables in the configuration space. I can encode the possible values of my random variable at a given time t into the diagonal entries of an n by n matrix A of t. You can compute expectation values using the density matrix in the standard way that we get from the Born rule. If A of t happens to be a projector, or a rank 1 projector, it describes a true or false question with true being 1 and 0 being false, and then this general rule becomes the Born rule. Okay? Now, of course, in quantum mechanics, we can measure more things than just diagonal matrices. There are non-diagonal operators that we can also measure. And the question is, what is their status? Well, if you model the measurement process, and again, I don't have time to do this, but it's in the paper, and I can describe it in the question session if you have questions. But if you model the measurement process, in a physical way, with a measuring device just being another system interacting with a system to be measured, and you just evolve the overall system, what you find is that your measuring device, if you set it right, can measure beables, but it can also measure things that look like beables, but actually are not representing ultimately what's going on in the system. They're measuring emergent patterns of the dynamics, exactly the way that Niels Bohr described in his follow-up to the EPR paper in 1935. Okay? So these emergibles are emergent effects that come from the interaction of the measuring device with the system being measured, and they're represented naturally by non-diagonal self-adjoint matrices. So you have non-diagonal self-adjoint matrices representing these emergent, observable-like things that are not really reflecting what's going on in the underlying system, together with the beables, which are in fact actual properties of the system, and together they form a non-commutative algebra, and this completes the textbook axioms of quantum theory. Okay, so we end up with this stochastic-quantum correspondence, according to which the Hilbert space formalism is basically like an analytical mechanics for stochastic systems. Just like we could use Lagrangian or Hamiltonian mechanics to describe Newtonian systems, we can use the Hilbert space formalism to describe stochastic systems. This correspondence, again, is many to one in both directions. A given stochastic system can have many Hilbert space representations. A given Hilbert space representation can represent many different stochastic systems. And again, this is just like how in classical mechanics, the Hamiltonian phase-space formalism is in a many-to-one correspondence with Newtonian systems. And like any form of analytical mechanics, you can now use the Hilbert space formalism for all kinds of purposes: designing systems to order, studying microphysical laws in a systematic way, studying symmetries, calculating predictions, and so forth. Okay. So now I'm going to talk about causal locality. So here's the conventional wisdom on causal locality. Right? Depending on whom you ask, you may hear any of the following conventional wisdom. No-go theorems, like Bell's theorem, have ruled out hidden variables altogether. In fact, in the press release to the 2022 Nobel Prize that was given for experimental work on Bell inequality, the press release says this is what their experiments did. It ruled out hidden variables. Okay? Another answer you might hear from some people is that, well, hidden variables theories are possible in principle, but they entail non-locality or non-local causation, so we don't want them because they entail non-local causation, and if we don't have them, then quantum theory is causally local. Sometimes you'll also hear from people, no, what they imply, the no-go theorems implies that quantum theory is just unavoidably non-local or causally non-local, and hidden variables are immaterial to whether it is or is not. So these are all just different statements. They're not compatible with each other. They're all widely disputed. And interestingly, what Bell's theorem, according to Bell himself in his papers, he was advocating the third option. So I see all the time physicists saying, oh, well, what Bell's theorem says is you can't have hidden variables, you can't have them because they lead to non-locality. That's not what Bell said. Bell said that there just is non-locality, full stop. There's no way to avoid the non-locality, and that's what he was trying to prove. Okay. But I'll be challenging that assertion in this talk. Okay, so let's talk for a moment about what we mean by non-locality. In Newtonian physics, I know what we mean by non-locality, right? What non-locality means is you've got forces, and some forces involve action at a distance. Newtonian gravity, for example, says that two bodies exert forces on each other instantly across any distance. Coulombic electric forces are the same. I know what this means. I know what non-locality means in this circumstance. The problem is that in quantum theory, we don't have forces anymore. Forces are not fundamental in quantum mechanics or in stochastic processes. So if we don't have forces, it's just not clear what we're supposed to mean by non-locality anymore. What is it supposed to mean now? The claim of this next part of the talk is that Einstein, Podolsky, and Rosen, and later Bell, introduced a proxy for non-locality called non-local causation that they hoped would capture what non-locality was supposed to be about. And the claim is that this was incorrect. And that means all the results based on this idea are fruits of a poison tree. But the question is, can we look to causal influences to determine, can we use causal influences to talk about non-locality? That's what EPR, Einstein, Podolsky, Rosen, and Bell tried to do. Okay, so quantum theory involves probabilistic rather than deterministic relationships between observations. So again, there isn't a tight linkage between purported cause and effect pairings. Now, there's a theorem in quantum mechanics that says that whatever your view on non-locality in quantum mechanics, you cannot use it to send controllable signals. That's a thing we already know. And some physicists say that's actually enough to mean quantum mechanics is local. But there's still these lingering questions that Bell was trying to address. Okay? Not immediately obvious whether quantum theory involves non-local causation. Okay. Now, there's a case to be made that causal talk is just folk science. After all, most of our physical theories, at least after Newton, involve differential equations that don't seem to involve cause and effect at all. So maybe causation is just folk science. It's not physically fundamental. This was the view in a paper by John Norton, a philosopher of science at Pittsburgh, which I recommend. But in that case, asking whether quantum theory is fundamentally causally local is meaningless. If you don't believe causation is really a part of nature, then what does it mean to say that anything is causal or non-causal? But let's take seriously the idea of people who take, who want to talk about causal locality. And along the way, I'm going to show how to make quantum theory a hospitable domain for causal influences and argue that it is locally causal. So I'm going to start with a very simple attempt at a definition of causal locality. Causal influences cannot propagate faster than light. The problem is that this doesn't tell you what a causal influence is. No one is trying to say what that is, and I'm going to try to provide that definition in this talk. Okay? But notice that this is a condition on any causal influences that happen to occur. Whatever causal influences there are, they shouldn't be able to propagate faster than light. I'm not asserting that in some circumstances there should exist causal influences. I'm not saying that in certain circumstances there must be a causal influence. I'm just saying that any causal influences that happen to be there cannot go faster than light. Okay? And this is a very important distinction made by a philosopher of science named Wayne Mervold in a paper in 2024. All right. What did Einstein, Podolsky, and Rosen do in their famous EPR paper? Can the quantum mechanical description of physical reality be considered complete? They used a rudimentary version of what Schrodinger shortly after called quantum steering. In simplified form, we get two particles. They've been prepared initially in some entangled wave function when they were close together. Then they are separated, because you can only entangle things when they're in proximity to each other or there's an intermediary between them. So assuming they're close together, we entangle them, we separate them. Right? And then we have Alice, let's say over here, measure one particle with some observable, and the collapse will then be to one orthonormal basis in the Hilbert space. And what happens, according to the textbook axioms, is the other particle necessarily collapses to the same orthonormal basis. And so Alice can kind of steer which basis Bob's particle over there collapses to. If she picks one basis, then Bob's particle will collapse to that basis. If she picks a different basis, Bob's particle collapses to that basis. It's like she's steering Bob's particle using collapse. Okay? She can't control exactly which state Bob's particle gets. She can't control which state she gets, but she can control the basis it collapses to. Right. No communication theorem prohibits the first observer from actually using this to send a message, because the first observer cannot control which result she gets and can't exactly control which exact result Bob gets, but she can at least steer which basis you get. Now, Einstein, Podolsky, and Rosen took for granted that there could be no causal influence from one particle to the other on the assumption they were very far apart. So they were using a notion of causal influence here. And the fact is that some quantum-steered wave functions are eigenstates of certain observables. Right? If Alice steers correctly, she can get Bob's particle to collapse to a basis where it has a definite eigenvalue of a definite observable. And if Alice is not really doing anything to Bob's particle, then what EPR argued is Bob's particle had to have known all along what those values were. Values not reflected in the wave function, therefore quantum mechanics is incomplete. Okay. Now, you could attempt to read the EPR argument instead as actually saying that the first observer is non-locally affecting the other particle. So really what EPR is setting up is an option. Either you have non-local causation, or there must be hidden variables, extra ingredients in the wave function that know in advance what Bob's particle is going to have. So what EPR sets up is a fork, a logical fork. Either non-local causation or hidden variables. Okay? If you allow non-local causation, this would be a manifest example of what Einstein called spooky action at distance. But this reading is contestable because it relies on some questionable notions. It relies on wave function collapse, which is not fundamental in some pictures of quantum theory, like the kind I've presented here, and also relies on what's called an interventionist conception of causation. It requires saying that what it means for causal influence to exist is the statement, A causal influence is B precisely if an agent, an observer, intervenes on A and therefore causes a change in B. That's what an interventionist theory of causation means. But agents and interventions are not fundamental things. If you cannot phrase this notion of causation at the level of the individual atoms, if you can't phrase it without talking about a sentient agent doing an intervention or a measurement, I don't know that this is a fundamental notion of causation. So there's some questionable things that show up in the EPR paper. What did Bell do in his famous 1964 theorem in this paper? He was inspired by the EPR argument. His paper was called On the Einstein-Podolsky-Rosen Paradox, and he was trying to deal with his fork, hidden variables or non-local causation. And what Bell tried to show was that hidden variables do not let you escape non-local causation. Even if you include hidden variables, you still have non-local causation. People have misread this to say that what Bell was showing was hidden variables alone imply non-local causation. And without them, you have local causation. Bell wasn't trying to do that. Bell took for granted that EPR had shown that without hidden variables, we have non-local causation. And Bell was trying to close the gap and saying that even if you have hidden variables, you still have non-local causation. To that end, Bell considered what are called measurement deterministic hidden variables, in which the hidden variables dictate specific measurement outcomes as occurs in Bohmian mechanics, which is a manifestly non-local theory with non-local forces in it. Bell's goal was to show that the second problem of the fork could ultimately not save causal locality. You couldn't save causal locality by introducing hidden variables. Here's the setup. Lambda will represent the hidden variables, the hidden extra parameters that are not captured by the wave function that tell you exactly what you get from measurements. A and B, which can have values plus or minus 1, are far separated measurement outcomes. And little a and little b are local measurement settings, local settings that the two observers, Alice and Bob, can set before they do the measurements to decide which observables they're going to measure. The assumptions for what Bell took to mean local causation are manifestly interventionist assumptions. He assumed that whatever the outcome for A was could depend on the hidden variables and only on the measurement settings Alice is using. And the outcomes for B could only depend on the hidden variables and the measurement settings that Bob was using. Bob's outcomes could not depend on Alice's measurement settings and vice versa. But this requires observers doing measurements. This is an interventionist notion of causation. Okay. Now, these assumptions apply the following expression for the statistical average or expectation value of pairwise products measurement outcomes. So the idea is we set this experiment up 10,000 times. We do it 10,000 times. Each time, Alice and Bob make their measurements with their measurement settings. And then when they're all done, they come together and they both take their first measurements, multiply them together. Then they both take their second measurements, multiply them together. They both take their third measurements, multiply them together. They multiply all 10,000 pairs together and they average. And the claim is this is the average they get, right? This is an average of products averaging over all the hidden variables which we imagine maybe change or fluctuate according to some probability distribution over the 10,000 runs of the experiment. So rho lambda is the standalone probability distribution of the hidden variables. Even assuming that they have a well-defined probability distribution is a big assumption, but we'll leave that. Notice there's a crucial factorization that appears here in the integral. You need this factorization to derive what we'll see as a Bell inequality. It's ironic that Bell's results hinge on assumptions about expectation values because earlier Bell had identified a flaw in a no-go theorem by von Neumann that seemed to rule out hidden variables altogether. Bell showed there was a flaw in that argument because von Neumann had made an unjustified assumption about expectation values. Just a note, Bell was not the first to do this. Greta Hermann figured this out almost immediately after von Neumann published his book with this argument, but Greta Hermann was completely forgotten, and her contributions to physics were mostly not recognized. She left actually physics shortly after this and joined the resistance of the Nazis, which arguably was a very good use of her time and all of our time. Okay, but using this formulation for expectation values, Bell was able to prove his famous inequality, an inequality that relates these expectation values. He argued any theory obeying his causal locality assumptions had to obey this inequality. Quantum theory predicts this inequality is violated. Experiments were done that confirm quantum mechanics indeed predicts the violation. And again, the press release said this means that quantum mechanics cannot be replaced by a theory that uses hidden variables, which is completely wrong. Anyway, Bell's 1964 paper therefore appears to rule out any locally causal measurement deterministic hidden variables. The hidden variables tell you exactly what you get from your measurement outcomes. What are the implications of this argument? Well, provided you don't take the EPR argument to be definitive, what Bell's 1964, maybe because you don't believe in wave function collapse, you don't believe in the interventionist conception of causation, Bell's 1964 argument leaves open several possibilities. You could have non-locally causal measurement deterministic hidden variable theories, like Boltzmann mechanics, where a pilot wave and non-local forces determine everything that happens. You could have hidden variables that don't tell you exactly what you get from every measurement, but only tell you probabilistically you get from every measurement. So the final measurement results are not just functions of measurement settings and hidden variables, but are probabilistic. You could also imagine formulations of quantum theory that attempt to eschew hidden variables altogether, like textbook quantum theory. But textbook quantum theory paints no picture at all of reality. When particle physicists talk about electrons whizzing around, that's all just color. The textbook axioms paint no picture at all. Bell's 1964 argument certainly does not rule out hidden variables altogether. And then, crucially, in 1975, Bell attempted to generalize his 1964 theorem to encompass the second and third possibilities, to rule these out as well, to capture measurement stochastic hidden variables theories and textbook quantum theory and show that they were also non-local. He also, and he didn't say this explicitly, but found a way to get around relying on interventionist causation, and this was crucial. So his 1975 theorem, which was more general, applied to all theories with stochastic measurement outcomes with or without hidden variables, and that includes the textbook theory. His goal was to show that all empirically adequate theories of quantum theory involve non-local causation. One big problem was, what the heck do you mean by causation now, with no interventionist causation? Bell didn't know. The second problem is, without all those assumptions, you don't get a factorization in the expectation value formula. You get a formula that looks like this, without clean factorization, and you cannot derive the Bell inequality. Right? There's no factorization anymore here. It's crucial for deriving the Bell inequality. So what was Bell going to do? Well, he describes what his process was a bunch of years later, 15 years later, in a lecture in 1990. The lecture was called La Nouvelle Cuisine. He said he started with the following principle, which is very similar to our principle. The direct causes and effects of events are nearby, and even the indirect causes and effects are no further away than prevented by the velocity of light. Very similar to our principle. But then he goes on to say, this principle is not yet sufficiently sharp and clean for mathematics. Really what he's saying is this principle doesn't give me the inequality. So he had to find another statement that would give him the factorization he needed. And so he states the second principle. But before he states it, he includes a very important warning that people have not read and they should internalize. Now, it is precise in cleaning up intuitive ideas from mathematics that one is likely to throw out the baby with the bathwater. So the next step should be viewed with the utmost suspicion. He says this, and people don't just skipped over it. His ingredients now are beables, lambda, beables, which can include measurement outcomes. It can include the wave function itself. He's not assuming that measurements are special in any way. A and B are far separate in measurement outcomes. He's more general now. They can take on any values between -1 and 1. They're also beables. A and B are, again, local measurement settings. We can regard all of these in non-intervention terms as just beables, ways the universe can be. Here are Bell's new local causality assumptions. He assumes that there is a rich enough collection of local beables in the overlap of the past light cones of A and B. That is, you take all of the events that could, by special relativity, send signals to A and B, and in that overlap, in that part of space-time, there's a rich enough set of variables, treated as beables, lambda, those are the beables, such that when you condition on them, you screen off from the conditional probabilities for A any dependence on the outcome B or the measurement settings for Bob. And similarly, the other way around. For B, the lambdas in that past light cone are rich enough that when you condition on them, they screen out for Bob any dependence on Alice's result or Alice's settings. Okay? Now, it is a general fact of probability theory that we have the following partial factorization. And so if you combine Bell's local causality assumptions with this general statement about how conditional probabilities work, you get the following factorization. When you condition on lambda, the beables in the past light cone, the correlated probabilities split up, they factorize into a part only involving Alice and Alice's settings and the hidden variables, and only the part involving Bob. This is the factorization that Bell was trying to reverse engineer with his assumptions. Okay? We get our factorization. And with this factorization, we get a factorization in the probability formula. We get the Bell inequality, actually a nice generalization of it that first derived by Klauser, Horn, Shimoni, and Holt in 1969. And so any measurement stochastic theory that satisfies Bell local causality assumptions is ruled out by the same experiments that won that Nobel Prize. Bell concluded that all theories, including textbook theory, involve non-local causation. Here's the problem. Bell's new principle of local causality tucked in a new implicit assumption. As manifest in that factorization form, Bell apparently didn't know about this. This is not in any of Bell's writings, but Reichenbach, philosopher of science, in a posthumous book in 1956, published what he called the principle of common causes. This says that if A and B are variables that are correlated, their joint probabilities do not factorize, and neither one causally influences the other, whatever causal influence means, then what Reichenbach's principle says is there must positively exist a new causal influence, a new variable C, that is the common cause of A and B, and when you condition on C, C is allowed to be put into a conditional probability formula, and when you condition on it, it causes the probabilities to factorize. In words, we have the assertion that there must exist, over and above what you had before, a common cause variable with a causal influence on A and B that screens off the correlation and leads to this factorization. This is stronger than just causal locality as we had been defining it earlier, but Bell needs it to get his theorem. Okay? This is Bell's criterion, which is equivalent to this factorization. This is exactly Reichenbach's principle, with the local beables in the past overlap of the past light cones being asserted to exist to give this screening. They are the Reichenbachian common cause variables. Okay? So essentially, because Bell did not have a concrete theory of causal influences, he didn't know what causal influence was, he couldn't use intervention as causation anymore, he just assumed that whatever reasonable theory of causation you might imagine, whatever reasonable causal local theory should entail this factorization as a downstream consequence. So in the absence of having a complete theory, he simply relied on what he thought was an inevitable requirement of any such theory. Okay? Now there's a terminological distinction here I keep mentioning. Causal locality is the more basic condition that any causal influences that exist can have to respect the speed of light. Okay? It doesn't assert that there must exist causal influences in certain circumstances. Local causality, the thing that Bell was using, is a stronger condition. He says that in some circumstances, there must exist common cause variables, there must exist causal influences that do a particular thing. That is a stronger statement. Now there are good reasons to doubt Reichenbach's principle. It may seem intuitive, but that's not a good reason for assuming that it's true. It assumes every common cause is a particular kind of variable that is a variable that can be conditioned on, that does certain things. That's actually pretty strict. And as Bill Unruh, theoretical physicist, wrote in 2022, I'm just going to summarize this. He says, interactions in quantum mechanics are clearly responsible for entanglement, but interaction is not a variable. Interaction is not something you can screen on, you can't condition on it. Quantum mechanics has things that cause entanglement that are just not of the kind of thing that Bell was trying to assume. Okay? Interactions are not Reichenbachian variables. So we have good reasons to doubt it. Now, there are other arguments purporting to demonstrate non-local causation. In addition to EPR, there's also the famous GHD thought experiment. There are various generalizations of the Wigner-Friend experiment. All of them make additional assumptions that are questionable or that violate indivisibility. None of them can be trusted. So it's really not clear how you would derive the Bell inequality or prove any of these theorems when working at the level of the atoms that make up measuring devices. I will note that advocates of the many worlds interpretation, or Everett and quantum mechanics, already deny that the premises of Bell's theorem are the right way to capture locality. However, arguably the many worlds interpretation is still non-local for reasons I cannot talk about right now. But anyway, I'm going to introduce a new notion of causality. This is the last part of the talk, and I will show that this new formulation exploits the loopholes I've mentioned, provides an actual definition of causal influences at the microphysical level, one that does not imply Reichenbachian factorization, and therefore avoids the conclusions of Bell's theorem. Okay? And this idea comes from the theory of Bayesian networks. So the first step is to note a key connection with another theory. In the theory of Bayesian networks, you consider a collection of random variables related by a collection of basic directed conditional probabilities. This is just a graphical representation. We've got random variables A, B, C, and D, and the arrows refer to causal influences. But the causal influences have a very concrete meaning that I'm going to tell you what they are. Here we have a simple Bayesian network with 4 random variables, A, B, C, and D. And the arrows mean that my network supplies in its laws, in its nomology, nomology means laws, the following conditional probabilities. Conditioned on the value of B and C and D, we get the conditional probability for A. The model supplies this as it's part of its fixed laws. Okay? We call A an endogenous variable and B, C, and D the exogenous variables. The exogenous variables can fluctuate from run to run or instantiation to instantiation, and then these laws dictate what the fluctuating values of A are. Okay? Now, in a concrete instantiation of this Bayesian network, because B, C, and D are allowed to fluctuate, they'll have some contingent, some instantiation-dependent joint probability distribution that may vary from run to run. But then given those, there is a multilinear relationship that then tells you what the probabilities are for A. So one can define other conditional probability distributions from this model, but they're not going to have the same basic nomological meaning. So in other words, you might go, well, I have these conditional probabilities. Why can't I use Bayes' theorem, this is just Bayes' theorem, to construct other conditional probabilities? Here I have a conditional probability of B given A, C, and D. Why can't I just construct this one as well? Well, the problem is that to construct this one, you have to take the nomological ones provided by your model. You have to take contingent joint probabilities that depend on each run of your model. They're not fixed features of the model. And you have to combine them into this messy, non-linear, complicated formalism. And that means that these new conditional probabilities you're trying to construct do not have the same status as fixed features of your model. They're not laws. They're not baked into the model the way that the Brown ones are, the ones that were built into the model. So the Brown ones really are special. And they mean that there is a directedness to these conditional probabilities. There's a directedness from B, C, and D to A, and we cannot reverse that directedness by having A, C, and D imply B without messing up what we mean by our conditional probabilities. There is a sense in which these conditional probabilities are directed. Okay? They're more fundamental as laws of the model. Crucially, Bayesian networks have been a non-interventionist causal reading. If a model supplies a basic directed conditional probability, like this one, then any stochastic fluctuations in B, C, and D dictate stochastic fluctuations in A, and I will take this to mean that B, C, and D are exerting causal influences on A, and you can't invert this by turning it around because then, like I said in the previous slide, you don't get fundamental conditional probabilities in the model. Okay? Notice how the directedness of these nomological or law-like conditional probabilities nicely captures the asymmetric nature of cause and effect relationships. Causes and effects, not effects and causes. Right? There's an asymmetry there. This captures the fact that there are causes, there are effects, and they have an asymmetry, but it does it without preferring an arrow of time, which is an open question. Like, one of the problems in the metaphysics of causation is there appears to be an asymmetry in causes and effects, but the basic laws of physics, for the most part, don't distinguish past from future. Most of the laws of physics are either exactly or at least approximately time reversal invariant. So how can there be a fundamental notion of causation which is asymmetric, given that the microphysical laws of physics are almost exactly time symmetric? Well, this is a notion of directedness that does not involve time at all. So it threads a very thin needle. Now, these models that propose these Brown, these fundamental directed conditional probabilities are exactly like the conditional probabilities that define the indivisible formulation of quantum theory we're talking about, right? Our indivisible formula of quantum theory is just a Bayesian network of exactly this kind, with laws that are not differential equations. They're laws that are phrased in terms of directed nomological conditional probabilities, right? So not only do we get a hospitable domain for causal talk, you can arguably apply causal reading to these nomological conditional probabilities, and this motivates a new theory of causation. On a theory X, to say that variables B, C, etc. have nomological causal influences on a variable A is just to say that the theory X specifies in its basic fixed laws a conditional probability of the form P of A given B, C, etc., read as the nomological conditional probability of A given B, C, etc. So this is an actual theory, a fundamental theory of causation I'm presenting here, right, which arguably answers some basic questions we have about causation, but it also happens to be the way that this new formulation of quantum theory is phrased at its deeper level, and so we can actually regard quantum theory as a nomological theory of causation par excellence. With this definition of causal influences, I can now answer the question, is quantum mechanics locally causal or non-locally causal once and for all? So consider a unistochastic system consisting of two subsystems Q and R. The overall system will have nomological conditional probabilities, right, from time 0 to later time t, where Q naught, R naught are initial configurations, QT, RT are the other configurations of the other time t. My definition will be that Q, subsystem Q, is free of causal influences from subsystem R over the time interval from 0 to t in question, if after marginalizing over the configuration of R, the resulting conditional probability distribution is no dependence on R naught. So if we marginalize over R, we sum over R, then the dependence on R naught vanishes, and we just get laws alone for Q alone. This is what I'm going to mean by freedom from causal influences. That when I marginalize over the other system, my original system has its own self-contained causal probabilities that don't depend on R. Now we can state an improved principle of causal locality, and arguably better than Bell's. A theory with microphysical directed conditional probabilities, like the formulation of quantum theory that we've been talking about, is going to be called causally local if any pair of localized systems, Q and R, localized in space, that remain at space-like separation, remain far apart in space, in the given situation, can never exert causal influences on each other, in the sense that the directed conditional probabilities for Q are independent of R and vice versa. That is, if they're far apart, then they satisfy that condition, that criterion for causal locality that I talked about. Now it's just a straightforward calculation to show that this principle is satisfied. You just check that it's satisfied. This is just a calculation. Consider two systems at space-like separation. By construction, their time evolution operators have this tensor factorization. This is a standard rule for quantum dynamics. We mod square the entries to get the entries of the corresponding unistochastic matrices, and then we do the marginalization, and the marginalization comes up perfectly. The theory is causally local. Okay? By contrast, suppose that Q and R are not kept at space-like separation. Suppose they are allowed to interact locally at some interaction time t prime. Well, then we fail to get this factorization. We'll fail to get this factorization of the stochastic conditional probabilities. And again, because the overall stochastic matrix for the overall system, as I explained before, encodes cumulative statistical effects starting at 0, at least until the next division event, we get a breakdown of factorization. We do not get causal. We get causal influences between the two systems. The two systems are exerting causal influences on each other, stemming from their local interaction at t prime. Okay? But notice that the interaction at t prime responsible for those correlations is not a Reichenbachian variable. It's not a thing you can stick into any conditional probability supplied by the theory. And finally, we can revisit the EPR argument. Alice and Bob, okay? Alice is this world line here. Time is up, space is sideways. Alice is staying put. She's just staying still. As time goes by, she traces a vertical world line. Bob is far away. He traces a vertical world line. He's not moving either. The two particles, Q and R, begin together in the same location. They interact with each other, and then they go their separate ways. Q goes to Alice, R goes to Bob. And now we have Q and Alice on one side, and Bob and his particle on the other side. Notice that the particles did interact in their past light cone. But Alice, in this whole experiment, is outside the light cone of Bob and vice versa. Well, you can now show by a straightforward calculation that Bob, and whatever Bob does not exert causal influences on Alice. If you marginalize over here Bob, you get isolated conditional probabilities for just Alice. Her conditional probabilities depend on her initial configuration A naught and the initial configurations of the two particles, but they were in her past light cones. That's perfectly fine. The only causal influences on A come from Q and R, which are both in its past light cone as expected. So to conclude, consider a stochastic process over a fixed orthogonal basis without imposing all the intricate nomological structure of a textbook stochastic process. You get an indivisible stochastic process, and you get quantum theory. One then seems to have a causally local, hidden, or physical variables theory based on simpler axioms than textbook quantum theory, arguably without a measurement problem and deflating a lot of the exotic talk about quantum phenomena. There are many prospects for future research directions, which I hope to discuss with many of you: applications to dynamical systems, stochastic processes, new algorithms for quantum simulations, new ways to think about quantum causal models, which are a quantum mechanical generalization of classical causal models, implications for some old metaphysical problems in statistical mechanics, ramifications for algebra-first approaches to quantum theory, generalizations of quantum theory. Now that we're not starting with Hilbert spaces, we're starting with a completely new set of axioms. We can imagine totally new generalizations of quantum theory that would have been impossible to imagine before, and maybe new possibilities for quantum gravity, which I'm particularly excited about because I come from a background in quantum gravity, and I can talk about those later if we've got time. So thank you. That's the end of my talk. Thank you very much.